So previously we have looked at Pourbaix diagram. We have looked at some special lines such as the sloped dashed line for hydrogen evolution, the sloped dashed line for oxygen reduction. We also look at the horizontal line for redox reactions that do not involve proton or hydroxy group. Now let's look at a line like this, line 3, that represent line 3, this vertical line that represent pure acid-base reaction that does not involve redox reaction or charge transfer. Line 3 representing pure acid-base reaction that does not involve redox reaction or charge transfer. Okay, so on the left side is iron 3 plus, and on the right side is iron 2O3 or ferrous oxide. To write the reaction, we would have iron 3 plus combined with water to form iron 2O3 and 6 proton. Okay, let's check the balance. 2 iron on the left, 2 iron on the right. 6 hydrogen on the left, 6 hydrogen on the right. 3 oxygen on the left, 3 oxygen on the right. 6 plus of charge on the left, 6 plus on the right. So in terms of mass and charge, this equation is balanced. Okay, and to understand it a little bit more from electrochemistry point of view, to help us determine the exact location in terms of pH for this line, let's rewrite this reaction a little bit. In this case, we add iron 2 plus, actually 2 of iron 2 plus, 2 iron 2 plus iron to each side of the above reaction. Add 2 iron 2 plus to each side of the above reaction. Okay, and then let's look at the part in red. Okay, which is, I would call it anodic or oxidation half-cell reaction from iron 2 plus to form iron 2O3, ferrous oxide. Iron 2 plus, 2 of iron 2 plus combined with 3 water to form iron 2O3 to 6 proton and release 2 electrons. This would be the anodic or oxidation half-cell reaction. Let's check again. 2 iron on the left, 2 iron on the right. 3 oxygen on the left, 3 oxygen on the right. 6 hydrogen on the left, 6 hydrogen on the right. 2 times 2 plus, 4 positive charge on the left, 6 plus and 2 minus, for the net would be 4 positive on the right. So the charge and mass are all balanced for this anodic or oxidation half-cell reaction, essentially going from iron 2 plus to form iron trioxide. Okay, and if you check the standard electrode potential series, the standard electrode potential for this anodic for this half-cell reaction would be 0.728 volt versus SHE. At the same time, the cathodic or reduction half-cell reaction would be for iron 3 plus to become iron 2 plus. Iron 3 plus combined with electron to form iron 2 plus. And similarly, the standard electrode potential for this redox pair or for this half-cell reaction would be 0.770 volt. You get this from standard table, and again it is with SHE. Okay, so we have anodic and cathodic half-cell reaction. If we add them up, of course the goal is to eliminate electron. You have to time a factor of 2 to both sides of this cathodic half-cell reaction to get the overall reaction. Okay, and the overall reaction for the cell potential would be, as we learned before, cathodic minus anodic. The standard electrode potential for the cathodic half-cell reaction minus the standard electrode potential for the anodic half-cell reaction. And in this case would be cathodic 0.770 minus anodic 0.728 volt. And we would get a standard cell potential for this electrochemical cell to be 0.042 volt. 0.042 volt. That gives us the standard cell potential for this electrochemical cell. Okay, still we are looking at line 3, which is pure acid-base reaction that does not involve redox reaction. But as we said, if we write the reaction in a slightly different way, we add 2 iron 2 plus to both sides, we can separate this reaction into two parts, anodic half cell and cathodic half cell. We said at equilibrium, the standard cell potential would be 0.042 volt, and the Nernst equation gives us the cell potential would be standard cell potential minus, if at 25 degrees C, 0.0592 volt divided by N, the number of electron transfer, times log of equilibrium constant equals, all this would equal to 0 at equilibrium condition. Okay? At equilibrium condition, the cell potential must be 0. And the Nernst potential gives the cell potential to be E0, standard cell potential, minus a factor times log of reaction constant. And if we rearrange, we would have N times E0 equals 0.0592 volt times log of equilibrium constant. Again, remember earlier we said this overall reaction can be separated to anodic half cell. Okay, iron 2 plus give out electron to form iron 2O3 solid, and the cathodic half cell, which is iron 3 plus, combined with electron to form iron 2 plus. And the number of electrons transferred would be 2, because to add them up, you have to time a factor of 2 to the cathodic half-cell reaction to cancel the electron, which means the overall number of electrons transferred would be 2. Then we would have the log of equilibrium constant would be Ne0 divided by this 0.0592 volt. N we said would be 2. E0 we said from earlier calculation is 0.042 volt divided by this 0.059 volt give us to be 1.42, which means the equilibrium constant, its log with base of 10 would be 1.42. And what is equilibrium constant? Equilibrium constant would be the activity for product. Activity of iron 2O3 times activity of proton, but raised to the power of 6 because of this stoichiometric factor of 6. And then in the denominator we have activity of iron 3 plus, but raised to the power of 2 because of the stoichiometric coefficient of 2 here, times activity of water, but also raised to the power of 3. Okay, this whole thing, reaction constant, take log, would be equal to 1.42. That's what we got. And for solid iron oxide, iron 2O3, we said generally the activity is taken as 1. This term would be 1. For solution, the solvent water would also quite often take the activity of 1, which means this term also become 1. This term for iron oxide is 1. This term for water is also 1. Then we are left with something simpler. We said, okay, this Pourbaix diagram is for 0.001 mole of ionic species, which means for iron 3, the activity for such dilute solution would be approximated by concentration divided by standard concentration, which turns out to be 0.001. Unitless. Remember, activity is always unitless. With all these, we can simplify this equation. 6 for proton activity becomes 6 times log of proton activity. Iron oxide activity is 1, water activity is 1, so times 2, a factor of 2 in the power term becomes the 2 in front of the log 1 over iron 3 plus activity equals 1.42. And then we would have pH, which means negative log of proton activity would be this term 2 times 1 over 0.001, that's 1000, taken log would be 3. 2 times 3 minus 1.42 move to the left side, and then this term move to the right side divided by 6. We would have the pH would be 0.763, 0.763, which would be the line between separate iron 3 plus from iron 2 plus. Okay. Sorry, the pH separate iron 3 plus from iron trioxide. That's a vertical line here, and the pH value, if you go down, this is 2, this is 1, a little bit less than 1, 0.763. Okay.